So U45 is a pretty large group, although not large in the grand scheme of things, but certainly takes a long time to write all the elements. What's the order of U45? How could I have figured out the order of U45 without listing all these elements? What's the secret sauce? What's the function that tells me how many relatively prime numbers to 45? Euler 5 function is worth spending some more time on just to make sure that we're completely familiar with. How do we figure out what the Euler 5 function of 45 is?
We do 5, 9, 5, 5.
Yeah. The same way that we figured out the isomorphism class of these groups, we factor the number 45 into a product of relative primes. So 5, 9 times 5, 5. Right? And because the Euler 5 function is multiplicative across relatively prime factors, 545 is the same as 5, 9 times 5, 5. And then each of those we can compute individually. So phi of 5, because 5 is prime, how many prime factors, how many numbers less than 5 are relatively prime to 5? 4 of them. Yeah, exactly. 1, 2, 3, and 4. All of them will be relatively prime to 5. Meanwhile, phi of 9, this is the power of an odd prime, right? 5, 3 squared. And so we have this power, this prime power formula that we can use. It's 3 to the 2 minus 1 times 2 minus 1. So that's 3 times 2. That's 6. And so we get 6 times 4, 24. And hopefully we've accounted for all 24 of those elements up here. So this is a group whose order is 24. And the big question, so the big thing that we're doing here at the end of the course is asking questions like, what kinds of groups of order 24 exist up to isomorphism? In the universe, what kinds of possible groups of order 24 are there? And that's a tough question to answer. It's a really tough question to answer in general. It's a question that we don't want to answer. So we can't, in general, unless we really are hardcore group theory fanatics that have read the entire, or at least understand the entire classification theorem for finite simple groups that takes like 1,000 pages to state and prove. We're not to that level. I'm not to that level. So instead, let's at least make a comment that what do we know is true about U45? What kind of a group is it? We don't necessarily know that it's cyclic, but we do know that it's what? It's abelian. After all, what's the operation in this group? Multiplication of real numbers, modulo 45, right? That multiplication is a commutative operation. So this is an abelian group. So that at least helps us to cut the question down to which abelian group of order 24 is it isomorphic to? Is it isomorphic to? So this is the point at which I'm just going to invite you to give me some examples. What are some examples of abelian groups of order 24? Z24 is the first example that should come to any of our minds, probably. The easiest way to make an abelian group of a specific order is just to take the cyclic group that has that order, right? Which is isomorphic to the group of integers under addition modulo 24. So 0, 1, 2, ... up to 22, 23 as an additive group, right? Additive group mod 24. So that's definitely an abelian group of order 24. It's also what kind of group? Cyclic. What's an example of a generator for Z24? 1 is definitely an example for Z24's generator. But here's another question that we haven't thought about for a little while. How many of the elements in Z24 are generators of Z24?
Aren't all of them except for 0?
Ooh, good question. So what would the cyclic subgroup generated by, let's say, 3 look like? Yeah, what's wrong with 3 as a potential generator? It divides 24, and therefore what's it going to generate? Only multiples of 3. We're not going to get a multiple of 2, for example. Well, we're going to get some multiples of 2, but we're never going to get 2 itself, for example. 21, right? So not every non-zero entry is going to be a generator. How many generators will there be? All these generators, what's the order of a generator in Z24? 24. It's got to have the same order as the order of the group because it has to generate every single element. So how many elements of order 24 exist in a cyclic group? What answers that question? Euler phi also answers that question. So I could say here that the number of generators is phi of 24, right? Because this is the number of order 24 elements. Phi of 24. And so now we've got another Euler phi problem to do, right? Factor this into a product of relatively prime factors. 24 is 8 times 3, so it's phi of 2 to the power 3 times phi of 3. And then phi of 3, since 3 is prime, is going to be, and phi of 8, you can check phi of 8 separately and show that it's equal to 4. But the point is that there are actually 8 different generators for the additive group, mod 24. I just wanted to throw this in here just as another reminder of what the Euler phi function can do for us. So by the way, that would mean that if U45 were isomorphic to Z24, that would mean that U45 would have how many? How many of these would be generators if this were a cyclic group? 8. There would be 8 of these, which if I took their increasing powers, the first power, second power, third power, and so forth, up to the 44th power, would give me all the different elements of U45, if U45 were a cyclic group. But of course, Z24 is not the only abelian group of order 24 up to isomorphism. What's another example? Z4 direct product Z6. So there's another example. By the way, I'm going to use external direct product here. Z4 external direct product Z6. That's a group of order 24. My question is, do we know whether or not that is a cyclic group? How do we know it's not?
Because the highest LCM is going to be less than 24.
Yeah, very good. So this is the benefit of understanding the isomorphism class of a group, is that now we can say with some certainty what are the orders of all the elements in this group. And the orders of any element in Z4 direct product Z6 are going to be what?
LCM of points.
Yeah, the orders of elements are going to be least common multiples of divisors of 4 with divisors of 6. I'm going to kind of write that as LCM of something which is a divisor of 4. After all, because Z4 is a cyclic group, it has elements of every order that is a divisor of 4. So there exists an element of order 1, an element of order 2, an element of order 4, all in that Z mod 4. Right? Same thing with Z mod 6. There's an element of order 1, 2, 3, and 6 in that Z mod 6 factor. So if I take the least common multiple of one of these and one of those, what's the highest least common multiple that we can get from this list? So in other words, this group, Z4 direct product Z6, does not have any elements whose order exceeds 12. And therefore it doesn't, in particular, have an element of order 24, which is what we would need for it to be a generator. Right? And so that means that this is not, in fact, cyclic. Right? So we know for sure, for example, that Z4 plus Z6 is not isomorphic to Z24, because this one is cyclic, that one is not. Yeah?
Do you mind just...
So these two examples, but then there's also Z2 direct product Z12.
But isn't that going to be isomorphic to Z4?
So yeah, there's a question. Is that a different group than the one that we just listed? Let's see if we can figure that out. Are there elements in Z2 direct product Z12 whose order is 12?
Yes.
Sure. Are there elements whose order is 24? No, for the same reason that there weren't elements of order 24 over here. Are there elements of order 4? Yeah. Are there elements of order 6? Yeah, I think so. Because we can find all of those over here in Z12. So this is actually an interesting question. Are these two groups the same? Or are these two groups not the same? What are some other possibilities? I'm going to leave that hanging for a second.
Z3 and Z8?
Z3, direct product Z8. So what can you tell me about Z3 direct product Z8? Does it, let me ask this first, does it have an element of order 24?
Yes.
What would that element be? What's an example as an ordered pair? How about 1, comma 1?
Yeah.
Right. That 1 in Z mod 3 has order 3. The 1 in Z mod 8 has order 8. And so the ordered pair has order equal to the least common multiple of 3 and 8, which is 24. So
Is that isomorphic to Z24 then?
yes,
They need to be
exactly,
relatively
exactly,
prime.
exactly. So that's what happens with Z3 plus Z28, is that it's a perfectly valid abelian group of order 24. It just happens to be isomorphic to C mod 24 because it's a cyclic group whose order is 24. So we can list it, but we're not listing anything new by listing Z3 plus Z8. But Z2 plus Z12 we cannot conclude is isomorphic to Z24 because these aren't relatively prime. 2 and 12 aren't relatively prime. What if I drag in a third factor? What about Z2, Z2, Z6? What do we think about whether this is the same as or not the same as anything we've already got up here on the screen? Is it cyclic, first of all? Does it have any elements of order 12?
No.
No. How do we know? Yeah, the highest LCM that we can make out of any divisor of 2, any divisor of 2, and any divisor of 6 is 6. So this new group doesn't have any elements of order 12, whereas these did. So this new one is definitely something new. And it's still an abelian group of order 24. Our big question that we're building toward, is going to be the capstone of our semester, is by doing this process of just listing out all the possible ways to factor our number, 24 in this example, into a product of things that are not relatively prime one to another, right? Like 4 and 6, 2 and 12, 2, 2 and 6. Is that process enough to guarantee that we've listed every possible abelian group of that order? Right? Is this thing that we are just doing right now the way to classify all abelian groups of a given order? It turns out that the answer is yes, and that's chapter 11. That's where we end the course on our high note in a couple of weeks. It turns out it's a theorem called the fundamental theorem of abelian groups, which says that this is the only way to up to isomorphism characterize what an abelian group of a given order looks like. And of these examples, only this first one is cyclic. These other ones are not. So let's go back to U45. If we take all the numbers from 1 to 45 that are relatively prime to 45, so if the greatest common divisor of A with 45 is equal to 1, then I can ask Sage for what is the multiplicative order of that element. And what that means is, how many powers of this element does it take before I get back to 1, the multiplicative identity? So this nifty little Sage script is going to list all of our elements of U45 and tell me what their orders are. So here they all are. So what we'll see from this is that U45 has got some elements of orders 1, 4, 6, 2, 3, and 12, right? But no element of order 24, which we knew, right? Because we decided it wasn't, well, actually we didn't know that. Let me roll that back a second. What does the fact that there's no element of order 24 in U45, what does that tell me? That U45 is not cyclic, right? We would need to have an element of order 24 here in order for this to be a cyclic group. Okay, but now let's go that step further. Maybe this will help to resolve our question about the other two groups. How many elements of each order are there? So the orders that we see here are 1, 2, 3, 4, 6, and 12. Let's just do a count of how many elements of order 1 are there. Yeah, that's always 1, right? Number of elements. After all, the identity is unique, right? And the identity has order 1. Okay, how many elements of order 2 do we have? There's 1 there, and there's 1 there. So there's only 2 elements of order 2.
Aren't there 3?
Are there 3?
26, 44.
19. Oh, here we go. 19, 26, 44. Ah, so there's 3 elements of order 2. Interesting. Okay.
Didn't we have, is that just for cyclic?
All right, now that we go higher than order 2, what do we know, by the way, about how many, without even counting, Can we say anything about how many elements of order 3 there are? There's 2, and that number has always got to be what kind of number? For the number of elements of order higher than 2. Not prime, necessarily. In fact, never prime. Because, in fact, these numbers all need to be even. There are always an even number of elements of a given order greater than 2. Because every element has the same order as its inverse.
Yeah.
And when the order of that element is not 2, the element and its inverse are different from one another. Right? So therefore, as soon as we cross this threshold, the numbers of elements of each given order have to be even past this line. Yeah, let me run that through again. This, by the way, was a fact that was used in the solution of a couple of homework problems on homework 7. I want to say it was homework 7. This is because, I'll just write it down, every element whose order is greater than 2, every element of order greater than or equal to 3, first of all, is unequal to its own inverse. Because if it were equal to its inverse, what would its order be? 2, or possibly 1, right? So that means that all the elements whose order is not 1 or 2, they come in pairs of an element and its own inverse, and an element and its inverse have the same order. Every element has the same order as its inverse. So I have a nifty diagram for that. I have nifty diagrams for a lot of things, I think, but as its inverse. So it's like if we're partitioning out all the elements in my group. I can have individual elements come in here that have order 1 or order 2. I can have as many of them as I want to, right? A, B, C, they come in by themselves, and these elements are all their own inverses. But once I cross this threshold, every element here is going to come in along with its inverse, which is different. So all the elements are coming in pairs when we cross that line. So that explains, for example, why we've got, 2 elements of order 3 in this group? Elements of order 4, we've got 1, 2, 3, 4 of them. And then we have a bunch of elements of order 6. 1, 2, 3, 4, 5, 6 elements of order 6. And that makes everything that's left over in order 12. 1, 2, 3, 4, 5, 6, 7, 8. So here's a full list of how many elements of each order there are in U45. I'm just using Sage to do all of the ugly computation for us. So now let's go back to our list of cyclic groups, our list of abelian groups of order 24. Z24, which we ruled out because it's cyclic. Z4, direct product Z6. Z2, direct product Z12. And Z2, direct product Z2, direct product Z6. 226, right? All right, so we ruled out Z24 because it's not a cyclic group. Which other one of these possibilities can we rule out based on the data we have now? The last one. Because?
Except it has order greater than.
Right. There's no element of order 12 in this group, and there's clearly a bunch of elements of order 12 in U45. So now the choice is between these two. So now let's see if we can take those two groups and figure out, maybe let's take one of them. Let's take Z2 direct product Z12. And let's figure out how many elements of each order that group has got. I'm going to take this U45 example and shunt it off to the side here for a second. Order 1. So order 1 is going to be the identity elements. There's only ever always 1. What about elements of order 2? Where are my elements of order 2 going to come from in Z2 direct product Z12? So I'm kind of thinking of here, I want the least common multiple of S and T to be equal to 2 for S dividing 2 and T dividing 12. What are my possibilities? Of a divisor of 2 and a divisor of 12 whose least common multiple with one another is equal to 2.
2 and 3.
No, least common multiple of 2 and 3 would be 6.
Oh, yeah. 2 and 1.
2 and 1 are the only possibilities. So I could take the non-trivial element from Z mod 2 and the identity element from Z12, so 1 comma 0, if you like, that would be an element of order 2. What's the other possibility? Well, there's two other possibilities. 1 comma 2, right? So identity element here, and 6, which is my element of order 2 in Z mod 12. But then 2 comma 2 would also have least common multiple of 2. So actually, I'm just going to list out. I'll list out these elements. So
Did you say 2 comma 2?
1 comma, I said, or what I meant was order 2 in this
order
group
2
and order 2 in that group, yeah. So 1, 0, 0, 6, and 1, 6. Those are 3 different elements in Z2 plus Z12 whose order is all 2. But those are the only elements of order 2 because there's no other elements of order 2 that I can pick from these groups other than the number 1 over here and the number 6 over there. But that's 3. That's a total of 3 elements of order 2. So far, this looks promising. 3 elements of order 2. How many elements of order 3 are there going to be? So now, again, we're looking for how many divisors of 2 and divisors of 12 have a least common multiple between the two of them of 3. Well, first of all, what's S got to be? If it's a divisor of 2 and least common multiple with the, yeah, S has got to be 1 in this case. So the only way to get an element of order 3 in this group is to choose the identity element, 0, over here, and an element whose order is 3 from Z mod 12. How many elements of order 3 are there in Z mod 12? I think there's only 2. That's because that's, after all, that's the Euler phi function of 3. 4 and negative 4. Right, so 4 and 8. 0, 4 and 0, 8. Those are my 2 elements of order 3 in this group. And so sure enough, we also have the same number of elements of order 3. And so we could keep going. Let's maybe skip to the end. If I skip down to the end, how many elements of order 12 are there going to be? If I have a divisor of 2 and a divisor of 12 whose least common multiple is equal to 12, what are the different possibilities? There might be a lot.
3.
So, but I don't have a 3. So S can't be 3 because it's got to be a divisor of 2. So S can be 1 or S can be 2. Right? That's really the only divisors of 2 that we have to work with. But if S is 1 and the least common multiple is 12, what does that make T? If S is 2, then, except that the least common multiple of 2 and 6 is not 12. Some of you said that it was on the last quiz. Many of you, in fact, said that it was on the last quiz. But if S is 12, what does T got to be? In order that the least common multiple be 12. Because 2 and 6 doesn't work because its least common multiple is 6. 2 and 4 doesn't work because its least common multiple is 4. 2 and 3 doesn't work because its least common multiple is 6. What's the only divisor of 12 whose least common multiple with 2 is equal to 12? 12. That's the only possibility. So how many such elements are there? Well, how many elements of order 12 are there in Z mod 12?
2.
There's 2. Well, there's probably more than 2. After all, this question is answered by the Euler phi function of 12. Okay. So number of order 12 elements. And this is 4. So there's 4 elements of order 12 that I could pick from this factor. And there's 2 possibilities for what I can pick in my first factor. And those choices are independent of one another. So how many elements of order 12 do we have in total? 4 times 2. So it certainly seems like we're painting a picture here that Z2 direct product Z12 would appear to be isomorphic to U45, at least if all that matters are the orders of the elements, and we know U45 is Abelian, and so it has to be isomorphic to one of these, then we would suspect it's Z2 direct product Z12. But just to go back to what we already knew about U45, what was the more sophisticated way of figuring out the isomorphism class of U45? So yeah, not only is the Euler phi function multiplicative, but these groups are multiplicative. that it's isomorphic to, I'm going to write this as the internal direct product of U5 with U9, and write the equal sign here instead of an isomorphism sign. But then each of those, in turn, is isomorphic to a cyclic group, a Z group. So which Z group is U5 isomorphic to?
C4.
Because it's what kind of group? U5 is what kind of group? 5 is an odd prime. And the U group associated with any power of an odd prime is definitely cyclic. Right. So cyclic, and its order is given by the Euler phi function of 5, so it's a cyclic group of order 4. And then what about U9? Z6. Okay. Z4 direct product Z6. So that's interesting because it's not what we would have listed if we did Z2 direct product Z12. So maybe it's true that these two are in fact isomorphic, one to another. Let's see if we can justify that to ourselves. So one way of doing that would be to say, let's take this Z6 factor for a second. Is there a way to rewrite Z6 as a direct product of two U groups? Not U groups, sorry, Z groups. Z groups. What is Z6 isomorphic to as a direct product of Z groups? Z2 and Z3? Because those are relatively prime, right? So that's isomorphic to Z6. So another way to understand Z4 plus Z6 would be that it's isomorphic to Z4, Z2, Z3. Right? And 2 and 3 are relatively prime, so we can recombine them to get Z6. But what other pair is also relatively prime here? 4 and 3, which when I combine those together makes my Z12. So at last, we find out there is no difference between these two. And so whichever of these answers that you were to put down, like however you decide to write U45 as a direct product of Z groups, any one of these three is perfectly fine. You may have reasons in some circumstances or another, depending on where your abstract algebra takes you, to prefer one of these over the other. But up to isomorphism, they're all describing the same abelian group of order 24, which happens to be isomorphic to U45 and is not cyclic because it doesn't have an element of order 24.